start to.
If you don't say anything and we just
do you want me to say something to him?
No, because I seem like you're really smart.
Yeah, I like that.
Sample that one last.
Yeah, no, I want to feel like a god again.
A god? A calculus god?
Yeah, high school.
Can't spell.
Anti-idea.
Why am I writing in this color? Okay, antiderivatives. Here we go. Anti. All right, so if f prime of x is equal to 3x squared, what is f of x? What was the original function? That is an antiderivative. That's what we're asking. Stefan.
Like 1 divided by 3x, so cube.
Not quite. You're close. It's just x cubed, right? Right? If I say it's x cubed, does that make sense? What's the derivative of x cubed? 3x squared. Are we done? Is that correct? Is that all of them? That is not the entire answer. Because what if I had x cubed plus 4? What's the derivative of that? What if I had x cubed plus 5? What's the derivative of that? What if I had, see where I'm going here? X cubed minus 1. They're all 3x squared. So the technical answer that you should write is that it's f of x is equal to x cubed plus c, some constant. It could be any constant. Now, to find that constant, we'll do it later today. You need some more information, but we're not going to worry about that right now, okay? But you have to write x cubed plus c when you're doing an antiderivative because the derivative of any constant is 0, okay? We call c the constant of integration. Okay, so we would say this is the antiderivative of f of x. Okay, so we're going to introduce this new symbol. It's called an integral sign. This little wavy thing here. That is it up there. It's called an integral sign. It comes from the letter S. All right, you'll learn why it comes from the letter S. It stands for sum, but we'll learn that in 4.2, 4.3. All right, we can call this swoopy whoop if you want. Swoopy whoop, a very technical term. So this is called an integral. When you have that, it's called an integral. Thank you. F of x, the function inside, is the function being integrated. D of x is the variable of integration. Just like you had a variable of derivation, like when d of x, actually. dy dx, deriving with respect to x, you're integrating with respect to x. Because when you get to higher levels of math, and you're dealing with multivariable calculus, you might only be integrating with one variable, even though there's 3 actual variables in the equation. And so that, now, gonna have to write on a little line here. That equals capital F of x. This is just the notation that they use. Plus c. The capital F of x, this is the antiderivative of f. So you'll see this a lot as you move through the course. Antiderivative of f of x. Yeah, late May. You do have that big final. Okay, so today we're just going to learn some basic rules and then apply them and do some practice. Okay? So just like limits and derivatives had rules, there's some basic rules for integration. The integral of 0 dx. The derivative of what equals 0? That's essentially what I'm asking. Any constant. So that would just equal c.
So anytime we see that integral outside the thing,
Yeah. It means find the antiderivative.
it means find the antiderivative.
Yeah.
Okay. So why is it up front that we have to find the antiderivative
Of that function.
How does that relate to?
Well, that's more complex than what we're doing right now.
Yeah. I'm curious.
Well, you know what? By the end of chapter 4, you'll know how to interpret that and what it means.
Okay. That's my goal.
There you go. Okay. Integral of k x dx. Now I'm using k as a constant. I just don't want to use c. Okay, to represent a different constant. So just like in derivatives and limits, you can pull constants inside and outside of the integration sign. Okay, so I can pull this constant out like that. Right? Sometimes you want to put a constant in, sometimes you want to pull a constant out. All right, depends on what you're doing. So constants can come inside and outside. Trig, you just kind of have to know. But if you know sine and cosine derivatives, you can just work backwards. So what's the antiderivative of cosine? Sine function, right? But you have to say sine of x plus c. So what's the integral of sine function? Negative cos. Because what's the derivative of sine? It's just cos, right? Because that's how you can check these. If you just go, what's the derivative of this? Does it give you that? It does. Derivative of sine is cosine. But I can't write cos here because the derivative of cosine is negative sine. So I have to have a negative in front of the cos to cancel it.
Wait, so why does the 0, like for number 1, 0 dx, why is it equal constant?
Because what's the derivative of any constant?
0.
0.
Oh, I see. So. Yeah.
Oh, I see what it's saying. It's 0 times in your derivative, which makes it nothing. And that's
Yes.
It looks like soda.
Sodix.
Yeah, soda.
so.
That's
All right. So this is the rule. You told me that the derivative or the antiderivative of 3x squared equaled x cubed. I mean, plus c, but we were just focusing on this. How did you do that? What is the rule? Essentially saying x to the n to what? Stefan.
1 divided by n plus 1 x n minus 1.
Oh, you're so close. You said n minus 1.
Yeah, at the top like of x. Yeah. Plus 1.
Plus 1, yeah. So when you're doing the antiderivative, just like when you're doing the derivative, right? You drop the exponent down and take one away. If you're doing the opposite of subtracting is adding. So this is going to be x to the n plus 1. All right, that's, if this is my n, I add 1 to it, and I get a 3 here. But how come this 3 isn't here? It's because that 3 would be there, but you divide by your new exponent, which cancels those. Okay? So you have to divide by your new exponent, and then you put a plus c. Okay? So the antiderivative of x to any power is n plus x to the n plus 1 divided by that new exponent n plus 1. All right, we're going to practice it. Yep.
When you say divided by that exponent, you literally mean like the number itself.
The number itself.
Not an exponent form, but just
The number.
So something to the power of 2 would be divided by 2. Right?
If I said that,
I cannot do that. Okay.
x squared, I add 1 to the exponent and divide by that exponent. And then you can check it by going backwards. If I want to do the derivative of this, I need to get this, right? So you drop the 3 down. What now happens? They cancel. And then you take 1 away, and you get that. All right. And the last thing before we do some examples, I'll just write out a polynomial. If you have something that is separated with terms, addition, subtraction signs, you can break it up just like derivatives and limits into separate integrals. So you can do them each separately. Sometimes that is advantageous.
Like, what sort of instance would that?
I can't give you an example that wouldn't make any sense.
Eventually, so we just don't know how yet.
If you had, this isn't going to make any sense, but say you had something where, well, if I had this, I don't know how to integrate that function, but because there's an addition sign, I can do them both separately. I know how to do that one. That's easy.
Yeah.
And I know how to do that one.
Oh, see, that made sense.
Yeah. That's pretty straightforward, but you can scale those up, right?
Where did the 1 dx come from? Is that just from the
That's this one.
outside? Oh, it's from the 1?
Yeah.
Wait, so that one's a constant. Why wouldn't it just?
Well, we're still doing the integration. I haven't done the integration here.
Oh.
I'm just saying that you can take an integral sign that has a polynomial or anything with
And you can
addition,
factor it
subtraction,
out,
and you
so-
can just rewrite them as 3 separate integrals.
Oh, so that's not the answer.
No, that's not. Yeah. Now we're going to practice doing them. Okay? So those are your rules. Here we go. Purple. Practice. Okay, we'll start with a simple one. Number 1. Three x to the 5th dx. Do we care about the 3? No, because you can pull it out, right? It's a constant. So we just write the 3. And then look at the x to the 5th. What do? What rule am I going to use?
It's plus 1. Yeah.
You can use that one. So you add 1 to 5. What's 5? 1 plus 5.
So 6.
And divide by that new exponent. Simplify your fraction. 3 over 6 is tack on a plus c, and you're done. Well, look, you don't even have to show any of that. You can just write the answer, right? When you get good at this, you'll just do these ones. You'll just do in your head.
And that's fine. That'll be acceptable.
Yeah, because these are pretty straightforward.
If you want us to show our work on this, do you want us to write plus C after you do it?
Okay, so when I'm marking a test, you're gonna have to ask JM what he wants. Invariably, people will forget to put the plus C's, right? If you forget on every single question, I'll take 1 mark off.
It's kind of like forgetting to put the list on.
Yeah, exactly. It is important, all right? But I'm not going to penalize you on every single question. I would just say, okay, you need to remember to do this. 1 mark off or something. I don't know. But yeah, people always forget. I forget to do it sometimes. So, all right, second example. One over x cubed dx. What's wrong? If I asked you to do the derivative of this, would you leave it like this? What would you do? Yes, and that's what you want to do here too, right? Because we're adding or subtracting. Well, we're adding it, but or if you're subtracting an exponent, you might as well just rewrite it as a. So it's not 1 over. So we rewrite it as x to the negative 3 dx. Negative 3 plus 1? Negative 2. Divide by your new exponent. Negative 2. Put a plus c. You can leave it like that. You could write it like this. It doesn't really matter. They're all the same. Okay. Are we okay with that stuff? See? All right. No, we're good. No, I don't like 3. Primes. They think they're so fancy. We don't have to hang out with anybody else. All right. What's the problem with the way it's written? I can put that in your reference letter. Max is always 30 seconds behind in the conversation. You weren't listening? So you write it as an exponent, and then we got to add 1. What's 1 plus a half? And do not say 1.5.
Yes.
Don't write mixed fractions. Let's write impropers. We're all grown-ups here. Yeah. So x to the 3 halves, then you divide by your exponent. So you're dividing by 3 over 2. When you're dividing by a fraction, what do you do? All right, how do you check? You do the derivative, right? And see if you get the original back. And you can see if you drop down to 3 over 2, it's going to cancel with 2 over 3. All right?
So how does this give us the area underneath the curve?
Oh, you're not supposed to know that yet. For right now, we're just doing it because it's fun.
The simple enjoyment. Simple enjoyment.
Yeah. Enjoy the simplicity while you can. Because it's going to go like this. All right. What number are we on now? 7? So you added 4 plus the 1 you're missing gives you 7. That makes perfect sense.
Next one's gonna plus 4. Numbers of questions are exponential, right?
Negative 2 sine x
We can
dx.
just pull out that negative 2.
You can pull a negative 2 out. You can do it in your head if you want. All right, so I pull a negative 2 out. So now I'm just looking at what's the derivative of sine x. Yeah. Even I had to think about that. So it's negative 2 times, yeah, times negative cos x, which is plus,
C. I thought we were going to use K's.
no, k's, I just did k when it was inside because I wanted to, oh my gosh. There we go. I just used k because I wanted it when we were inside, just to differentiate it from c.
Oh, I see.
That was all, but it's still a constant, yeah. All right. What am I doing right now? 11. That's right.
Oh, wouldn't that just be 1? Wait, no. You didn't hear that.
C.
X. There we go.
It's x. X plus c. So what's the derivative of x?
1.
It's just 1. And it's like there's a 1 there. I just didn't write it.
This data just means that it
Yeah.
doesn't mean it has to be like all X.
That's right. What's the? Are we actually doing? We're not doing Fibonacci, are we? No.
I think we're at 13 with Roman numerals.
13 with Roman numerals. I was gonna go 18. I think I'm just gonna start adding the previous number to it. All right. 18.
That's 1.
I would have.
I am curious to know.
3x squared plus 4x minus cos x. So what, even though this looks like a weird function, why are we able to do it?
Because we can turn that into the integral of x times in each of the things.
Yeah, so we can just do each one separately, right? So what's the derivative of 3x squared? 3x squared, just this bit. That's it.
What's the derivative?
No, did I say derivative?
Yeah.
What's the antiderivative of 3x squared? Sorry. X cubed, right? No. You could do x cubed over 3 with the 3 in front of it, but they're going to cancel, right? See, I could go like this. Then those cancel.
So it's just useless to write. I see what you're saying.
If we wrote x cubed and a professor told us to show all of our work, would we get
I don't think they would for this level.
just
Then you'd have to show it. Yeah. But I don't think they would for this type of stuff. What's the antiderivative of 4x? Yes. Does that make sense? Does everybody understand how we got that? What's the derivative of, or I keep saying derivative. What's the antiderivative of cosine x? It's just sine, but because there's a minus in front, we're going to write minus sine x. Yeah. There you go. Oh, what did I forget? Plus c. And once you do the antiderivative, the integral sign, the swoopy doop, is gone. Because the swoopy doop is telling you to do the antiderivative. So once you do it, it disappears.
Wait, so is the dx and that is just like stating,
The dx is saying integrate it with respect to x. Because if you go on in math, you're going to see stuff like this.
Oh, heavens. What?
So you could have 3 variables, and you can integrate each triple integral with respect to x, with respect to y, with respect to z. So I know at this point you're like, why do we need the dx? It's notation so that if you go to higher level stuff, you know what to integrate with respect to. Okay, just to forget all that. That's like third year, second and third year stuff. That's second and third. Second or third year math. All right. Is that it? Oh, yeah, one more to do, and then I'll give you some practice. What number are we on now? -4. There we go. We're adding negatives now. All right. X plus 1 over square root of x, d of x. This doesn't look like anything we've seen before. So what do we do? Quotient rule. We're doing the antiderivative. Okay, you want to break it apart. How are you going to break it apart?
X divided by x
Root of x.
And then another one of just 1 over.
Yes, that's exactly what you want to do. This little trick here will save you a lot when we get into more complex things. Okay? And I don't want a square root, so I say x to the 1/2 plus 1 over x to the 1/2. When you have a single denominator, I cannot emphasize this enough. Divide it up. It will probably make your life easier, especially when we get into complex stuff, okay? So I've seen so many kids go down these rabbit holes, and it's a page of work that looks like an absolute, like the pencil just vomited all over the page. You don't have no idea what's going on, and it would, if they did something like this, it clears up pretty quickly. Okay? So if you have a single denominator, divide it off to both. Most of the time, you get a nice, easy integral to deal with. We got to simplify this, though. What is x over x to the 1/2? What do you do with the exponents? You subtract them. So then we get x to the 1/2 plus, what am I going to do with the next one? 1 over x to the 1/2. What do I want to do? Make a negative exponent. Now, that is nice and easy to deal with because we have no division. Like as soon as you have quotient stuff, a division, things are complicated. So you either want to rewrite it, and if you can't rewrite it, then we'll learn that you have to do a substitution and stuff later on. But that's why you want to rewrite first, if you can. All right, so what's the integral of x to the 1/2? And it just came to a grinding halt. Add 1.
Or x to the power of 3 over 2.
Yep.
Over.
And then you divide by 3 over 2. Plus, what's negative 1/2 plus 1? That's 1/2. Divide by 1/2. That looks gross. So what do we do with the denominators? Flip them up. So I get 2x to the 3/2 over 3 plus 2x to the 1/2 plus c. Yeah.
Because otherwise it just cancels.
Not always. Like. No, if you had like x, if you had this, I said, what's that?
Yeah.
Right?
But you said 5 minutes ago you don't need to write that.
No, if there was like a 4 there, you wouldn't have to because it would cancel, right?
4 is a constant.
Yeah.
Right? Makes sense. Okay, but otherwise, if 4 wasn't there, you have to.
Yeah, exactly. Okay, here's your practice questions. Page 251, numbers 11 to 25 odd. I still have some more stuff to do, so I'll give you a bit of time to work on those. and then we'll move on. So the integration sign basically cancels the derivative, right? The integration sign cancels the derivative, so you just get f of x. You can think of it that way.
Why doesn't it, like integrate just the original function?
You just get 1 degree higher function.
So if you
There's not really a name for it,
so if you took the
right? But you'll see it has to tie with what Ian was saying. That would give you the area under that curve. That's where this is going.
wait,
So
wait just a moment. So if you took the I word of the double prime, you get the
f prime.
F prime.
So if you did this, if you did the integral of f double prime of x, that gives you f prime of x plus c. Actually, we're going to do an example of that near the end. I'm going to show you. Okay, so what's the antiderivative of 3x squared minus 1? X cubed plus c, right? So this is called the general solution. Because we don't know what c is. All right? So it's just called the general solution. To get the particular solution, you need the other piece of information, which is this. F of 2 is equal to 4. So, what is my x value and what is my y value in that? Yeah, there's x, there's y. So I take my general solution and I say, well, if f of 2 is equal to 4, I put 2 in for all my x's. So 2 cubed minus 2 plus c equals 4. And then you solve for c. 8 minus 2 plus c is equal to 4. 6 plus c is equal to 4. So c is equal to -2. So my particular solution is x cubed minus x minus 2 is f of x. That is the particular solution. You got the general, where you have c. If you have an x and a y value, you can determine what the c value actually is. Okay? Is that all right? It's just one more little step you have to do. All I want you to do is page 250. I think it's 251 still. 35 to 41 odd. There are some double derivatives. So if you remember what Noah said, if you take the antiderivative of f double primed, you get f primed. So if you want f of x from the second derivative, you have to do the derivative again. Okay? Yeah. All right. So I think 39 and 41, you have to do that. So I'll give you 10 minutes, and then I want to show you an application in physics, how you get some of the physics formulas that you use in physics 11 and or 12.
Is that 250?
251, I think it is. Same page that you were on. All right. We have, I guess I have to unfreeze it. We have a ball that is thrown in the air with an initial velocity. You've all seen this is a math or a physics 11 problem, basically. With an initial velocity of 29 meters per second from a height of 40 meters, what is the position function of the ball, which we'll call h of t? So we know, we learned back when we did derivatives, that if you have a position function and you take the derivative of it, you get the velocity. And if you take the derivative of the velocity function or the second derivative of the position function, you get the acceleration function.
Wait,
So
is that actually giving you the velocity and acceleration? Like the exact? Like
well,
that?
in this example, I give it to you.
Yeah.
Okay, so if you throw something in the air, what's the acceleration?
-9.
Right, because gravity's pulling it down. So if I want to work, we have this acceleration, which is the derivative of velocity or the second derivative of the position, and I want to get back to the position. You guys just did some examples like this. You do the integral of the second derivative or the acceleration function. If I integrate -9.8 with respect to time now, right? Because when you throw something in the air, we're tracking it on a time scale. I get negative 9.8 t plus c. That is my velocity function. That's a general velocity function. But I know what the initial velocity is 29 meters per second, right? So that means when t is 0, the velocity is 29. So if I put that into here, 0 times 9.8 goes away. I get c is equal to 29. So now my specific velocity function is this. V of t is negative 9.8 t. I do the integral of that because I want to get the position function back. So I integrate it. I integrate negative 9.8 t plus 29. That gives me that function, right? You add 1 to the exponent and divide by 2. So t squared over 2, correct?
Yes.
29t, because you put a t in front of that, plus my constant. What does negative 9.8 mean? That's your acceleration. What is 29?
Your velocity.
That's your initial velocity.
Wait a minute.
So that's where that formula comes from.
Oh.
Sometimes it's written 1/2 at squared
Yeah.
plus v naught t plus h or whatever. That's where it comes from. All right. Those formulas aren't just like randomly made up and thrown together. They come from the calculus.
It's just a proof of them.
Well, you can't in grade 11. Like that's a grade 11 formula, right?
Yeah.
Physics 11.
You're
Like
not gonna prove
you can't. What do you like? You're doing parabolas in grade 11. Factoring stuff, right? You're not going to be able to understand that. So, anyway, just wanted to show you that calculus is the basis for all the physics and the chemistry and all the math behind all that kind of stuff.
Calculus the basis for the mole.
The mole?
The number. Where does that come from?
That's just a unit of measurement.
Okay.
Right?
Yeah. Like all the equations.
Those are just ratios to the big. Okay. Right? That's not really calculus. They're just doing ratios. That's why they don't have economics. Because you just throw things are not the same. We don't need you.
What?
We're getting old, so I think we go this way. At my peak. You're golden, right?
I can use that.
Doing that for you. No, that's what I'm having with
3.14, 5.9265258.
Yeah, like 16.
Let me just read it.
That's not, remember, that's what. I'm not gonna be here tomorrow.
Okay. Yeah, Tuesday.
You're like, oh, I gotta do my college stuff.
No one's ever going to be ripped. There's just a couple errors here.
That's fine.
That's
what I want.
Okay, first, EMCS.
Oh yeah, we gotta fix that.
And then I think some of those grades in there are incorrect.
Yeah, I wasn't sure about the grades.
And then there's just like these big gaps here.
Oh no, yeah, like I'm gonna change that.
Oh, okay.
Oh yeah, this. I was like, do you want me to put in like, do you have a job? Do you play
Oh, yeah.
hockey? Like,
Yeah, I play hockey, and then I work at Costco on the side of school.
what do you do at Costco?
Front end like cashier / packer.
Okay.
And then I also play the cello and
Cello?
and the piano and the saxophone. And yeah,
Don't most people just play one instrument?
most of the time.
Oh my gosh.
Yeah.
Okay.
So yeah, just
I'll add that stuff in.
okay.
When do you need this?
Like
tomorrow?
Tomorrow, yeah. It's like due at noon.
Okay, I got spare first block.
Okay. Do you have a bunch
Come-
more of these to write? I think a lot of people do this.
No, I just gotta fix Anthony's
Oh,
and
okay.
yours.
Okay.
I think I'll the other one. I think I'm done the other ones.
Okay. Sounds
Yeah. So I'll just add that in,
Mhm.
and I'll do Anthony's, and then so yeah, if you come see me tomorrow,
Mhm.
or if I do it tonight, I'll email it to you tonight.
good. Okay, that sounds good.
I
I was talking to Miss Harrington, and she said it would be better rather than getting a physical copy if you could email me one, and then I can turn it into a PDF to send them.
Okay.
So that
All right,
was-
I'll do that.
Okay.
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 All right, I'll add that stuff in.
All right, thank you.
Yep. Hanging out, Benna? Oh, your mom's picking you up? Where do you live?
I live in View Royal.
Oh, really? Where in View Royal? I grew up in View
Right
Royal.
next to Banfield Park.
Where's Banfield Park?
Like in View Royal.
Is it by? Is that by the pub? No, that's Portage, right?
No, it's by like there's like a bakery and a clothing store and Spiral Cafe.
Is that off the Old Island Highway?
I literally just moved there like a month ago. So
Oh,
I'm not
okay.
very aware of what else is around.
Oh, okay. All right. Did you live? You lived out here before, didn't you?
I lived in Mishnosa before.
Do you like it there, or is it just too new to know?
Yeah, well, I do like it. I like being close to